Let's continue. Next question है sin x into 1 plus cosine x is maximum when x equal to. So once again इसका डेरिवेटिव निकाल के 0 की इक्वेट कर देते हैं. So इसका डेरिवेटिव हो जाएगा cosine x into 1 plus cosine x plus sin x into negative sin x. So मैं इसको negative sin स्क्वायर लिख देता हूँ डायरेक्ट. So this is equal to 0. So that means cosine x plus cosine squared minus sin squared equal to 0. Okay. So cosine x plus cosine 2x equal to 0. So cosine 2x equal to negative cosine, which is cosine of pi plus x, pi minus x, whatever. So pi plus x. So 2x equal to 2n pi plus minus of this thing, so pi plus x. So this is going to be 2n minus 1 pi. So just some odd multiple of pi plus minus x, which means either we have x equal to 2n minus 1 into pi, or we have x 3x equal to that. So like x equal to 2n minus 1 pi upon 3. Okay, cool. So this is maximum when x equals to. So yeah, let's just see what we have over this. So first of all, you will have 1 pi, then you have 3 pi, then 5 pi, and so on. Well, so 2 pi, right? So that's actually the period, so we don't have to worry about these. Just have to consider this one. And then for this guy, you have pi by 3, you have 3 pi by 3, which is pi, so that's covered over there. And then you have 5 pi by 3, and the next one is like bigger than 2 pi, so we won't consider that. Okay, so let's see which of them gives the maximum value. So pi, that will give 0, so maybe that's not correct. Okay, pi by 3, that's going to give us square root of 3 by 2 into 1 plus 1 by 2, which is 3 square root of 3 upon 4. Okay, and then 5 pi by 3, 5 pi by 3 is pi minus pi by 3, right? 2 pi minus pi by 3, yes. So minus pi by 3 basically. So that will give sin x is like negative stuff. So negative of all this, yes. Cosine is still the same, so yes. That will be negative 3 square root 3 upon 4. So that will be the minimum, and this is the maximum. So this happens when x is pi by 3. Okay, next question. The curve f of x equal to x plus sin x has no maximum but has minimum. Okay, we know that as x approaches infinity, this approaches infinity. As x approaches negative infinity, this is negative infinity. Those negative infinity, infinity, those are minimum and maximum values. So it has neither minimum nor maximum. And if we talk about its derivative, does it have any local minimum maximum? So it will be 1 plus cosine x. It's always positive, which means it's an monotone increasing function. Next question. The maximum value of the area of triangle with vertices a comma 0, a cosine theta comma b sine theta, and a cosine theta minus b sine theta is. Okay, so let's write this. Okay, so this is weird. It's like you have a unit circle a, one point is in this direction, one point is like over there, and then another point is over there. So the maximum value of this thing, so this angle is theta. What's the, so this triangle, this small triangle over there, what's the maximum area of this triangle, right? So what's this distance going to be? This distance is just a minus a cosine theta, and this distance is a sine theta. So we just have multiplications like a squared sine theta into 1 minus cosine theta, and this upon 2, because, well, okay, so upon 2, but then that times 2 as well, so cancel that. It's just a squared sine into 1 minus cosine. Yeah. Oh wait, oh, it's actually the same thing as that, right? So sine x into 1 plus, just that over here you got 1 plus cosine x, over here you got 1 minus cosine x, but all in all it's kind of the same kind of thing. So this is once again it's gonna give us maximum when we have 3 square root 3 upon 4. So a squared into 3 square root 3 upon 4. I should be putting mods and stuff, but whatever. Oh, so you also have this b stuff over there. Okay, that's not nice. So this is not a sin theta, this is b. Okay, so this should be ab over there. So 3 square root 3 upon 4 ab. Next, this function has a maxima, minima. What does it have? Okay, take its derivative, so it should be 3x squared minus 3, okay, minus 6x plus 6. Okay, that's the derivative, which is just 3 into x squared minus 2x plus 2. Okay, so this is like 3 into x minus 1 squared plus 1. It's always positive, which means it has neither. Yep, neither maximum nor minimum. When x is in this range, the maximum value of f of x equal to x plus 6 power 4, 8 minus x cube is. Okay, think. Well, that's something. So when do we have the maximum value stuff? That's okay. How we can also like do this with, I think, something like AMGM, because these are positive numbers. X plus 6 and 8 minus x, these are actually positive. So if we can somehow make that, that will work, but okay, we don't want to do that yet. Anyway, let's just take the derivative and do it. So this will just be 4 x plus 6 cube into 8 minus x cube, okay, plus 3 into 8 minus x squared into x plus 6 power 4, but that into negative 1, so this should be negative over there. This equal to 0, that's the condition. So just have 4. So like take that square out and take that 3 power out, so there should be 1 over there. Okay, so 4 into 4 into 8 minus x equal to 3 into x plus 6. Well, looks like that. So this will just be 32 minus 4x equal to 3x plus 18. So 7x equal to 12 minus 8 is 4, and then 2 minus 4 is like 14. So x equal to 2. That's when you have the maximum or whatever the thing is like. Most likely it's just a... Well, let's see what it is. What's the second derivative though? Oh no, I don't want to find a second derivative. Oh, so we just want to find the maximum value and stuff. So yeah, just put x equal to 2 over there. Oh, the maximum value of f of x is, just put 2, so this should be 8 power 4 into 6 power 3, and that's this option. Next, if alpha beta are the roots of x squared minus a minus 2x minus a plus 1 equal to 0, then the least value of alpha square plus beta square is. These are the roots of this equation. Right, so a plus 1 into 1. That won't work. A minus 2, that's not what I want. You cannot actually factor a plus 1 into something like that. That will add to a minus 2. That's not possible. So then what? Think least value of alpha square plus beta square is, well, we just have to do it the old way. So alpha square plus beta square is just alpha plus beta square minus 2 alpha beta. Alpha plus beta, well, just negative b upon a, so yeah, it's just a minus 2 square. Wait, sorry. So 2c upon a, so c is just negatives, like 2 into a plus 1, a is 1. Cool. What's the least value of this thing? And does it actually say that these roots are real or anything, or like these are not complex or something like that? I guess alpha beta can be complex as well. So then this is purely yeah, it's purely dependent on a. It's not dependent on whether or not alpha beta are real. Anyway, so this should be a squared minus 4. Wait a second, why even do all that? Plus 2 into a minus 2, so minus 2 plus 2 plus 3 plus 6 over there. A minus 2 plus 1 squared, I think. Okay, plus 5. Yeah, that's right. So a minus 1 squared plus 5. So when a equals to 1, this happens, and at that point this is 5. Okay, that was nice. Did I do something wrong? Well, a minus 2 plus 2, that should give 3, and then that's gonna be 6. Okay, cool. So yeah, it's correct. Next, Rolle's theorem, or whatever this is called, Rolle's theorem cannot be applicable for. So f of x equals to square root of 4 minus x squared in minus 2 to 2. So it's defined at least. Okay. So what it states is that if you have the same value of the function at two different points, and there must be like some point in between that interval where the derivative is 0. So let's see, f of x equal to square root of 4 minus x square, we say. Oh, it seems like this. Think about it, the radius is 2 and is going from minus 2 to 2, somewhere over there. It's like this is x and this would be, yeah, that does make sense. Like, okay, so this is actually just a unit circle. So this circle thing is the locus. Okay, so why can't be the Rolle's theorem thing applicable? We know that if at 2 points it's the same value, then at some point, which we know is right over there, the derivative is 0. So it's applicable. What's the problem with that? I don't know. F of x equal to x squared plus 3x minus 4 in minus 4 to 1. I don't see why that would not be applicable. If that is the case, then okay, yeah, I mean, what's the problem? It has the minimum value at minus 3 by 2, which is in fact in the interval. So that means that yes, it is applicable. It's also continuous and stuff. So yeah. D, cosine 2x. Once again, another continuous function, 0 to pi. So it's like 2x goes from 0 to 2 pi. It has all values, right? So it can take all values that the cosine function takes, which means like, yeah, some of them will be repeated and stuff. So it's applicable. B, f of x equals to okay, this thing, greatest integer function of x. This is not continuous, so that like is obviously, it can be the only thing where you have some problem. But really, what is the problem? So f of x equal to this thing in minus 1 to 1. It's 1 to 1 is like that. So something like this, huh? This is 0 point over there. Minus 1 to 1, that would be like that. And why is this not applicable? Yeah, whatever. So it's just discontinuous. That's why it is like not so applicable, because the derivative is like not defined over there. So stuff can be bad over there. We can just like our the reasoning for why Rolle's theorem is correct is that if you want to go from, okay, so these are the two places where you have the same value of the function. So if you start from here and your derivative is 0, well then that's good. It's the derivative is 0, so no problem. But if your derivative is not 0, it's like positive or negative, whatever. At some point you must change your direction, because if you just keep going, you will keep on increasing, so you will never reach this thing. So you have to change your direction and then go like this. So your derivative will change from being positive to now being negative. So that means that since the derivative is continuous, what that means is that at some point your derivative was 0. So this only makes sense when derivative is continuous. If it's not, well, then what can we say? Like, for example, if I take let's think about a function that doesn't follow this rule. Well, the greatest integer function, I don't know, it's an increasing kind of function, so it's not making sense to do that over there. You cannot have the same values. I mean, of course you can have the same values when it's on one of those lines, one of the steps, but then the derivative is in fact 0 between them. So What should we take to demonstrate why this is not correct? Maybe the fractional part function. Yeah, that might be correct. Yeah, so the fractional part function, let's just take that for example. So these two have the same value, and then your derivative is positive over here and over here, but in this little region it's just not defined, so that explains it. Yeah, similarly, like for this function, for the mod function, the values are the same, but the derivative is not zero anywhere. At this point it's not defined, so we cannot say anything. So wherever it's like not defined, we I mean like that's kind of a problematic thing, so that's why this won't work. Okay, next question. Right, Rolle's theorem cannot be applied for cosine x minus 1 continuous function, so I guess it can be applied. X into x minus 2 square doable, sine squared x pretty doable. This would be the thing. Let's check this. 3 plus greatest integer function of x minus 1 to the power of 2 upon 3. 0 to 3. That's weird. 2 upon 3. Okay, so more like x minus 1 squared, like again greatest integer, that thing squared, and that to the 1/3 power. So it's positive at least. Oh, that's nice. It's positive. Oh, so yeah, like we could have also taken something like that mod of x square or something like that. Sorry, greatest integer of x square or something like that to show why this is not working. But whatever, you don't want to get invested in that. What's happening over here? It's just this thing to the square and then the 1/3 power. Okay, and 3 plus that. So this is like it has some kind of symmetry about the point 1. So for example, that at half and 3/2, yeah, those points look good. It has the same value. So at half this is having value like 0, and no, it's not having the same value. No. We just need to graph this. So let's see, 0 to 3. So from 0 to 1 is less than 1, so this is just some negative number, so the greatest integer will be -1. Yes, so -1 square, that's just 1. That to the 1/3 power is once again 1. So this is 3 plus 1, which is 4. Okay, then 1 to 2, this is 0. So just 3. Then 2 to 3, so 2 minus 1 is like 1, but bigger than 1 in fact. So okay, that would be 1. Since that's 1, this is going to be over here. Okay, that's how it is. So Rolle's theorem, like here the thing is that this derivative is like 0. Wait, what? Whatever, it's just not applicable because it's discontinuous, even if the statement looks correct though. Okay, the value of c in Rolle's theorem for f of x equal to natural log of sine x in this interval is the value of c. What c? I don't know what you're talking about. Really, I don't know. So okay, wait, maybe I do remember something. So a and b were the points where the values are same, and c, it was the point where the derivative was 0, right? Whatever, just say that it was a thing. So value of c in Rolle's theorem for f of x equal to natural log of sine x in this interval is, so pi by 6 to 5 pi by 6. Pi by 6 is pi minus pi by 6. So yeah, first it will increase, then it will decrease, and it's happening symmetrically. So let's just think about it like this: pi by 6, 5 pi by 6. When it's pi by 6, we just have 1 by 2. So this would be natural log of 1 by 2, which is a negative number. So somewhere over there. Okay. And then over 5 pi by 6 2, it's just this number. And then it is, okay, 0 over there. So it's like this. Okay, so that's how this would look. It's just touching at pi by 2. Okay, value of c, it's always going to be this one. Yeah, it's going to be pi by 2. Next question. The value of c in Rolle's theorem for f of x equal to natural log of x square plus ab upon x into a plus b. Okay, natural log of x square plus ab upon x into a plus b. What is this? What should I do with this? In a to b, so just symmetric or anything. When you put a over there, just a squared is like a into a plus b. Yeah, that would be 1, so that would be 0. And then when you put b over there, that's also 0. Okay, when is the derivative 0? The derivative is 0 when you have 1 upon this thing, which is x into a plus b upon x squared plus ab, this to be equal to 0, right? No, wait. But how? That doesn't make sense. When this happens, no. This only happens when x equals to 0, but when x equals to 0, this thing is kind of not defined, so that doesn't make sense. And when else does this happen? When else is this derivative 0? It never. It's not 0 anywhere else. Where x is bigger than 0. How? Its derivative, it's gonna be 1 upon that. Oh shit, no. This times the derivative of the inside stuff. Okay, so derivative of x plus ab upon x into a plus b. Okay. That should be equal to 0. This is not ever going to be 0, so don't worry about this. This is always positive, don't worry. Wait, sorry. The square thing, that square term will be erased, but whatever. 2x into x a plus b minus a plus b into x squared minus ab upon the square term, which we don't care about. Okay, so this would be 2x squared. Okay, that actually a plus b can get cancelled. In fact, we can just kind of cancel that over here itself, but whatever. So 2x squared minus x squared minus ab equal to 0. So x squared plus ab equal to, wait, what? Plus? No. Oh, this is supposed to be plus over there. This is supposed to be plus as well. This is supposed to be plus. This is supposed to be minus. X squared equals to ab. X equals to square root of ab, that's gn. Okay, if f of x equal to x cube plus bx squared plus ax satisfies the condition of Rolle's theorem on 1 to 3 with c equal to this, then ab is so at c equal to this thing, you have the derivative equal to 0. Okay, so just got 3x squared plus 2bx plus a equal to 0, and then this is the solution to that. Just gonna put that over there. 3 into 2 plus 1 by square root 3 squared, which is 4 plus 1 by 3 plus 4 by square root 3 plus 2b into 2 plus 1 by square root 3. It's a equal to 0. That's the first equation. Okay, so tired. Cancel the 2's away. No, we cannot do that yet. Really, they had to give us this 2 plus 1 upon square root 3 thing. Why? That's not fair. Satisfies the condition of Rolle's theorem in this interval. Wait, so at 1 and 3 this gives the same value? That's what you're saying? So at 1 this will give us the value 1 plus b plus a, and at 3 this will give us the value 27 plus 9b plus 3a. So these must be equal. I mean, like, obviously you cannot solve this with one equation alone, you need another equation for sure. So that's where the other equation comes in. So that would be 8b plus 2a plus 26 equal to 0. So 4b plus a plus 13 equal to 0. So a is minus 4b plus 13. Okay, cool. So let's just start checking this thing. Okay, b equal to 6, then a would be negative of, we'll just have 24 plus 13, which is 37. So negative 37, that is not the thing. B equal to 11, that also doesn't work. Did I miss something? It doesn't look like that though. This. It looks correct. What's the problem? These values must be the same, right? So you must have 8b plus 2a plus 26 equal to 0. So you just got 4b plus a plus 13 equal to 0. But then none of these values are matching up. So what's the problem? 11. What? Even what is this? Well, let's actually try negative 6 over there. So if b is negative 6, this would be negative 24 and 13. Yeah, that gives negative 11. So this is the only one that works. Okay, that was nice. But what about this? Maybe that was just to distract us. Next question. The value of C of Lagrange's mean value theorem for f of x equal to... do we really have to memorize all this stuff? Like the definitions of, I mean, the way in which it's presented. Do we have to memorize all that? That's not correct. I don't want to check it. Okay, the value of C of Lagrange's mean value theorem for f of x equal to natural log of x on 1 comma e is. So once again, this C is most likely the thing where you have the same derivative, like same slope or whatever the thing is. So Lagrange's mean value theorem, what does it say? I think it said something like roughly like this. So if these 2 points are there, you can connect a line, and this is the curve between these two. If this curve is continuous, then there must be some point where the tangent has the same slope as this line. Yeah, that's what it said. Okay, so f of x equal to natural log of x on 1 comma e. Let's try to graph this. So at 1 it is 0. This is 1. This point is 0. At e, this is 1. Okay, and it's natural log of x, so it reduces stuff, right? Yeah, so like something like this. Yeah, something like this, whatever. So we just want this slope. This slope is, this is 1, this is, shit, no, this is e minus 1, so the slope is 1 upon e minus 1, and this is 1 upon x, yeah, because that's the derivative, so x is e minus 1. That's when this happens. The value of C of okay, for f of x equal to x minus 2 squared in 0 to 2 is, wow. Okay, so at 0 it's 0, at 2 it's 0 as well. So if I had to graph this, it's 0, 2, these are 0. And what's the derivative though? Well, you know, the derivative has to be 0 in that case at C. So this is just going to be x minus 2 squared plus 2x minus 2. Okay, this should be equal to 0. Cool. So this happens at 2 places. It happens at 2 Okay, why at 2? At 2 this is 0. Oh, that's really nice. So 2 is like a minimum or maximum kind of point, but that's not the value that we want. That's not C. No. So x is not 2. It cannot be 2. That doesn't make sense. So the other option is x minus 2 plus 2x equal to 0. So you have 3x equal to 2x equal to 2 by 3. That's the other thing, and that's the C that we're looking for. The value of C of LMV for f of x equal to Lx square plus mx plus n on a comma b is the same kind of stuff, I think. Okay, we want the derivative to be 0, so just have x equal to negative m on L. That's when the derivative is 0, sorry, 2L. Okay, on a to b. Oh no, no, on a to b. Oh, sorry, m is not that. What am I doing? Okay, so L into a squared minus b squared should be there, so like a plus b. Wait, do we already know this thing? Yeah, we do. It's just going to be a plus b upon 2. Nice. A plus b upon 2. We already did this somewhere. Lagrange's mean value theorem cannot be applied for mod x. Well, yeah, it cannot be. Negative 1 to 2. It's like 1 over there, 2 over there. Yes, it cannot be applied. Okay, x minus 1 upon x in 1 to 3, it can be, except that at 0 it's a problematic thing, so it cannot be applied at that. Wait, okay, so we never actually had 0 in the interval. It's just from 1 to 3, so it can be applied, no big deal. Ln x from 1 to e, yes, it can be applied. It's going from 0 to 1, finite values, continuous. Yes. Square root of x minus 4 in 2 to 4, yeah, it's pretty doable. Next, the difference between the square roots of two successive natural numbers greater than n squared is the difference between the square roots of two successive natural numbers. Oh god, what am I doing? Okay, sorry, that I have not had sleep correctly. The difference between the square roots of two successive natural numbers greater than n squared. So there are two natural numbers, say n plus 1 and n, they are successive. The difference between the squares of these two numbers, well, that we know that's just going to be 2n plus 1. Okay, larger than n squared. So both of these numbers like are, wait, what? Sorry, square roots. What am I doing? Square roots of these numbers. Okay, larger than n squared. Oh, so these numbers, these successive numbers, these are larger than n squared. Okay, cool. Is, so what's the difference between these two? Okay, that was weird. Well, if you think about it, it can be written as 1 upon square root of n plus 1 plus square root of n as well. Okay, so this is definitely smaller than if there was 1 upon square root of n plus square root of n. So it's equal to 1 upon 2 square root of n squared, which is 1 upon 2n. Yeah, so it's less than 1 upon 2n, that's for sure. But really, why is this in a calculus section though? There must be something about it. Maybe like the square root function, it has to do with that. Difference between the square roots of two successive natural numbers. These let's talk about slopes and stuff. We know that the slope of that thing is covered somewhere over there. Oh, that might work. What's the derivative? It's like 1 upon 2 square root of x, right? That's the derivative of the square root function. So think about it. It's an increasing function, yes, something like this, looks like this. So this is n over there, sorry, this is like small n over there, and this is n plus 1. Okay, we know that somewhere in this interval we have the same stuff and whatever, but the real thing is that this slope this slope is always bigger than that, right? Because only then does it make sense to actually yeah, that must be the correct thing, right? This slope is always bigger than that. And what is this slope? It's this thing, 1 upon 2 square root of x. Okay, so what does that mean? It means square root of n plus 1 minus square root of n upon the x difference, which is 1, which is this slope. This is less than this slope, which is 1 upon 2 square root of x, but evaluated at n. So 1 upon 2 square root of n, which is like, yeah, correct. That's very nice. And n is greater than n square. Okay. N is greater than n square. Okay, so what about that though? Yeah, that's it. N is greater than n square. What do I even have to do with that? How can we put that over there? So does that mean like it would be like, okay, think. N is, so that would mean this is actually less than 1 upon 2 square root of n, because n is a bigger number, so square root of n square. So n is like a bigger number, so this complete thing is smaller and stuff. Yeah, that looks correct. So this would be less, which is equal to 1 upon 2n. So this is the inequality that we have, which is, yeah, this should be correct. Okay, let's check all this. Let's check this. Okay. Okay, exercise 1a. Wow, there's a lot that we have to do. How much time is it going to take though? It's still only done first exercise. Okay, let's check. First D, second A, third B, fourth C, fifth D, sixth A, seventh A, 8 C, 9 B, A D B. Okay, A. Oh wait, what? 11th D is correct. It's none. Wait, why? Why is that so? Okay, whatever. We will think about it later. 12th D, 13th B, 14th D, 15A, 16C, 17B. So yeah, cool. 18D, nice. 19A. Then you got B, D, D. Then the next should be BCC. So 24th, no, 23rd. 23rd is BCC, yes. 26th is C, that's also correct. Okay, 27th D. 28th DAB. 31st, okay, BCC. Yeah. 34th BBBC. 38th D. 39D. 40C. Okay, so that's all of it is correct. That's nice. Okay, except this one. The function 2x cubed minus 9x squared plus 12x minus 3 is increasing when x belongs to the interval. So if it is increasing, its derivative must be positive. So let's talk about its derivative. It should be 6x squared minus 18x plus 12. Okay, which is 6 into x squared minus 2x plus 3. Oh, wait, what? It's increasing when x belongs to the interval. That's weird. Wait. Now, No, something's not correct over here. 6x squared minus 18x plus 12. Yeah, that's the derivative. No big deal with that. Factor out the 6, so it should be x squared minus. Oh, minus 3x plus 2. What am I doing? What am I doing? Which is 6 into x minus 1 into x plus x minus 2. So if it's bigger than 2 or it's less than 1, then this thing is positive. So that's why it will be increasing. That's my reasoning. So why is B not correct and D is correct? Doesn't make sense. It's a cubic, yes, so it should be the correct thing, right? Whatever, maybe it's just a typo. Anyway, so see you people later.